Hello everyone, myself Dr. N.C.H. Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to the today's presentation on Stochastic Process Part 2. In the last session, I have introduced the concept of stochastic process and some examples and applications were also discussed. Now, what is a stochastic process? A process or a system that changes with time, according to time. Here, for example, for some t belongs to capital T, x of t. So, the random variable that varies with respect to time, and the process that involving the random variable which varies with respect to time is called stochastic process. And coming to today's presentation, today I am going to discuss about the dependent and independent stochastic processes. So, different types of stochastic processes, and also multi-dimensional stochastic process and classification of stochastic process and the probabilistic structure of stochastic process, and also we discuss about stationarity. Now, dependent and independent stochastic processes. In stochastic processes, the relationship among the members plays an important role. So, if you consider two members of the system, for example x1, x2, how these two members are related or whether they are related or not. So, depending on that, we can divide the stochastic process into two types: the dependent stochastic process and independent stochastic process. So, the relationship among the members plays an important role in stochastic process, and hence the stochastic process are described according to the nature of dependence relationship existing among the members. So, it depends on the relation that exists between the members, and basing on this, we divide the stochastic process into two types: dependent and independent. Now, coming to dependent stochastic process, if the members of the family are mutually dependent, so for example x of n, or we can denote it by xn also. If the members of the family are mutually dependent, mutually means if you consider any two pairs of values, for example x1, x2, they must be dependent. Similarly, x1, some x5, those also must be dependent. So, if the members of the family are mutually dependent, then the process is said to be dependent stochastic process. Otherwise, simply it is said to be independent stochastic process. Otherwise, it is said to be independent stochastic process. And we can define it as, for all t1, t2, etc., tn, the random variables x of t2 minus x of t1, x of t3 minus t2, so the next minus present, like that x of tn minus 1. If all these are independent, then the process is said to be independent stochastic process. So, if the members are mutually dependent, it is said to be dependent stochastic process, and if all these random variables are independent, then the process is said to be independent stochastic process. Now, multi-dimensional stochastic processes. Multi-dimensional. Here we are talking about the dimension of the variable. For example, if I consider only x, some x of t or xt, a single variable, that comes under general the stochastic process of dimension 1. And here let us consider two such values, x1t and x2t. So, these x1 and x2, here we have two values. So, this comes under the stochastic process of dimension 2 because there are two values. Similarly, we can define a stochastic process with three values, x1, x2, x3 also. then it comes under 3 dimension. So in general, n dimension means consider n values, x1t, x2t and so on xnt. This is a 2-dimensional stochastic process in continuous time having continuous state space. So this is a 2-dimensional stochastic process. If we consider n values, that comes under n-dimensional stochastic process. And now here a stochastic process is a function of sample points and also time. The stochastic process is a function of sample points and time. And here the sample points may be sometimes discrete or sometimes continuous. So that means in the case of a random variable, in probability we have discussed the random variable x is said to be discrete if it takes finite number of values. The random variable x is said to be continuous if it takes infinitely many values. For example, capital X equal to small x that lies between a and b, then it comes under continuous case. So depending on the random variable, whether it is discrete or continuous, here the stochastic processes can be classified into 4 different types. So this is the classification of stochastic process. Here there are 2 things, the sample point and the time t. So x and t. X is the sample point that depends on time t. So there are 2 things, x and t. If any one of these 2 is discrete, then the stochastic process is said to be a discrete stochastic process. If any one of these 2, x and t, is discrete. For example, if both x and t are continuous, then the stochastic process is called continuous stochastic process. So here both the sample point and the time t both are continuous, then the process is said to be continuous stochastic process. Now coming to this discrete stochastic process, if x is continuous and t is discrete, so you can clearly observe here, even though x is continuous, t is discrete. So therefore the process comes under discrete stochastic process. Similarly, if x is discrete and t is continuous, so here t is continuous but x is discrete. So again it comes under discrete stochastic process. If both are discrete, then also obviously it comes under discrete stochastic process. So depending on the sample point x and the time t, the stochastic processes are classified into 2 types, continuous stochastic process and discrete stochastic process. Continuous when both x and t are continuous, discrete if any one of these 2 is discrete, simply that comes under discrete stochastic process. So that classification is clearly given in the form of a table. So here the sample point x of t is continuous, discrete. There are 2 different cases for a sample point that can be discrete or can be continuous. Similarly, the time t is discrete or continuous. So if both x and t are continuous, then the process is continuous. Now you see here x is continuous but t is discrete. So this is discrete stochastic process. Similarly, here we have x is discrete but t is continuous, even though it comes under discrete stochastic process, and both are discrete. So again this is, if both are discrete, then it comes under discrete stochastic process. Now the stochastic processes can also be classified as deterministic and non-deterministic. So here deterministic, what does it mean? Can be predicted. We can determine, we can estimate, or we can predict. And non-deterministic cannot be predicted. So a stochastic process is classified into 2 types, deterministic and non-deterministic, basing on the whether the future values can be predicted from past observations or not. So, if all the future values can be predicted basing on the past observations. So, using the previous values, can we predict the next values? If it is possible, then the stochastic process comes under deterministic stochastic process. Non-deterministic stochastic process. If future values of any sample function cannot be predicted, we cannot predict the future values using the previous observations, then the stochastic process is said to be non-deterministic. So, in the title itself, deterministic means predicted and non-deterministic cannot be predicted. In the title itself, it has a meaning, or the definition is very clear. So, if all the future values can be predicted using the previous values, then the process comes under deterministic stochastic process, otherwise non-deterministic stochastic process. And coming to the probabilistic structure. So, here this concept is related to probability because it is involving the random variable x, and which depends on time, that comes under stochastic process. So, if there is a random variable, it takes some values, and also we can find the probability of the random variable at some particular value of that capital X. So, probabilistic structure of stochastic process. A random process can be defined in two different ways: a collection of different time functions, or else a collection of different random variables defined at different time instants. So, a probabilistic structure can be obtained using the collection of different time functions, or else the collection of random variables that depends on time instants. And a random process becomes a random variable when time is fixed. For example, if x of t, if I write like this, the random variable depending on time t, if time is fixed, there is no change in time, then simply I can write it as x, which is a random variable. So, the process becomes a random variable, there ends. If time changes, then it comes under stochastic process. So, a random variable is characterized by a probability function. If we have a random variable capital X, immediately you can find the probability of that random variable capital X. So, it is characterized by the probability function, and statistical measurements such as mean, variance, moments, etc. can be calculated for that random variable also, or for that probability distribution. So, here since x is a random variable, it is associated with some probability function, and hence we can calculate some statistical measurements also. Therefore, we can study the probabilistic structure of a random process. So, the study of probabilistic structure of a random process is possible since the entire process is linked with a random variable x, which has the probability function also. Coming to probability distribution function and density function. Now, here the probability distribution function or cumulative distribution function, whatever may be, both are same. Let us denote it by capital F. And probability density function, in shortcut we use PDF. This is small f. And in probability, in random variables and probability distributions, we have discussed the relation between these two, the probability distribution function and the probability density function. This small f, probability density function, can be obtained by differentiating capital F. So, the probability density function can be obtained by differentiating the probability distribution function. Similarly, if probability density function is given, you can find capital F of x by integrating the probability density function with respect to x, f of x dx. This is the relation between distribution function and density function. Now coming to this stochastic process, we can define the probability function as f of f suffix x of x1 comma t1. So in stochastic process there are two things, one is the sample point and the time t. So x1 at time t1, this cumulative or probability distribution function is defined as probability of x of t1 less than or equal to x1 for any real number x1. So this is called the first order distribution function. Similarly, you can define second order also. Second order means here in first order we have only x1 and t1. In second order we will have x1, x2, t1, t2. Similarly, third order x1, x3, x1, x2, x3 and t1, t2, t3 and so on. Now, this is the probability distribution function. That means capital F. Now, the probability density function small f is given by, just now we discussed, the small f is the derivative of capital F. So, differentiating capital F with respect to that x1, we will get the probability density function in the case of first order distribution. Similarly, in second order probability distribution, this is the second order probability distribution, and again by differentiating this, we get the probability mass function, probability density function in the case of second order distribution. And coming to the last topic of today's presentation, stationarity. Here, there are two things in random process. One is the stationarity and the transient one. Stationarity of a random process explains the time invariance of certain properties. So, time invariance, it deals with the time invariance. That means there is no change in time, then how the process will be. So, the distribution function or certain values do not change with time. So, in stationarity, the distribution function or else some values do not change with time. Hence, this stationarity can be defined as a process is said to be stationary if fx of x1 t1 is independent of time t1. So, simply I can write like this, no need of writing t1 because it is independent of time. Similarly, fx of x1 t1 and fx of x1 t1 plus delta both are equal. So, at time t1 and in the immediate instant t1 plus some delta, both the functions are same. That means the distribution function doesn't depend on time. That is stationary process. So, in this case, the mean of each random variable will be the same. In stationarity, the mean of each and every random variable is the same. Expectation of x of t is x bar, which is constant for all variables. So, stationary means when the distribution function do not change with time or the function is independent of time and the mean of each random variable is the same, that comes under stationarity. And evolutionary process. A process which is not stationary is called evolutionary, that comes under transient one. So, a process which is not stationary is said to be evolutionary. In today's session, we have discussed about the dependent and independent stochastic processes and also the classification of stochastic processes. So, there are two types, continuous stochastic process and discrete stochastic process. So, if either the random variable or the time t, if any one is discrete, then that comes under discrete stochastic process. If both are continuous, then it comes under continuous stochastic process. So, in the next session, we will discuss about the Markov process and the Markov chain, Markov process and Markov chains. So we'll meet in the next session. Thank you.